So I don't know if you ever played with dominoes when you were a little kid. Maybe you stacked like 20 or 30 or who knows, maybe 300 dominoes together and you try to make that domino train. And what happens when you flick the first domino, then the second domino would fall, right? And then the third one and the fourth one. And in fact, all of them would keep falling. So, until you've actually hit every single domino. Now imagine if you could make an infinite number of dominoes. And what if you stacked an infinite number of dominoes like this? Now here's a side view of a domino. So there's a domino on the page. Here's another domino. Here's another domino. Here's another domino. Here's another domino. A domino. A domino. A domino. Now you have an infinite number of these. So the way we're going to symbolize that mathematically is go dot, dot, dot. And why don't we label this first domino here? N equals 1, and then the second domino is n equals 2, and so on and so forth. So if you hit the first domino, you know that you started the domino train, right? You started the chain reaction of dominoes falling. So that's really, really important. You've got to be able to hit the first domino to actually see the nice chain of reactions. So the number one thing you got to remember, the first domino has got to be true, or it's got to be able to fall down. So I'm going to be able to say P of 1 is true. In this case, true means the domino will fall down. So true is equivalent to saying the domino will fall. Now, how do you make sure this will actually continue on forever? Suppose maybe you started somewhere else. Maybe you started over here. If we picked on the kth domino and you tipped that over, and let's say hypothetically you tip that to your right, are you able to make the next one fall? So maybe you didn't tip these dominoes here. Maybe you pick on the kth domino. Would you be able to tip the next one? So the other question is, if I hit the kth domino and falls, another way of saying that is P of k is true, right? Remember, true means the domino is fall. So true means the domino will fall, right? Does this imply that the k plus 1 domino will fall? So that is really the question. Maybe you're walking around and you're walking along the domino train and you didn't bump the first set of dominoes. Let's say you bumped the kth domino and you leaned it over to the right. Will the k plus 1 domino fall? Maybe on another day, all the dominoes are standing up and you knocked a domino over here. You knocked this domino to the right. Will that one fall over? Okay. So if we could answer that question, then we are guaranteeing that the infinite number of dominoes will continue to fall. So this leads us to a formal method of proving statements that are equivalent to the natural numbers. So we're going to say proving proving a statement, and we're going to use a notation for that statement called P of n. Proving a statement called P of n is true. It consists of 3 steps. 1, show that the statement for P of 1 is true. This is another way of saying show P of n is true for the very initial step. In other words, for n equals 1. This is sometimes called the base step. In other words, the first domino must be knocked over. The second step is a little bit more complicated. Suppose P of k is true. In other words, go ahead and assume that the kth domino falls down. Now you got to show that P of k plus 1 is true. And this is not obvious in math. It may be obvious when with you playing with dominoes, but this is where the work is very, very crucial. I'm going to add a third step that most authors will not include, but the third step is conclude that P of n is true for all n. In this case, in many cases, n stands for the set of natural numbers, or for every object in the set of natural numbers. Keep in mind that your base step doesn't always have to start with 1. Sometimes your base step starts with 3. So it could be these natural numbers. It could be 3, 4, 5, and then dot, dot, dot. Sometimes your base step could be 7, dot. Oops, sorry, you need at least 2. So 7, 8, dot, dot, dot. Often, if your base step is 1, then you hope that the next domino would fall, and so on and so forth, and then dot, dot, dot. But the key to guaranteeing that all your dominoes will fall is actually this second step here. Suppose that the kth domino is actually true, or P of k is true. Show that P of k plus 1 is true. In other words, the next domino will fall over. That's the metaphor here. Let's prove this proposition of n right here is true for n equals 1, 2, 3, dot, dot, dot. So remember, these 3 dots means there's actually an infinite number of equations here. This is not just one equation. There's actually an infinite number of equations. So you're going to prove a statement once for an infinite number of equations. So isn't that nice? You're not going to take every single equation and write a separate proof for it. I could illustrate what I mean with some context in just a few moments. I do want to remind you what this PMI stand for. This is called Principle of Mathematical Induction. And remember that the principle of mathematical induction requires you to have 3 steps. You kind of want to think of it as a metaphor for falling dominoes. So step 1, you got to show that the first statement or the first equation is true. The proposition is true for the very initial step or the base step. And in this case, our base step does start with 1. It doesn't always have to start with 1, but you can tell that it was given to you in this example here, and we are starting with the base step, which is n equals 1. The second step in the principle of mathematical induction is, suppose you bumped over the kth domino and that one falls. Now your goal is to show that the next domino will fall. So suppose P of k plus 1 is true. Third step is to show, I'm sorry, let me take that back. I said one thing and I wrote something else. I meant to say suppose P of k is true. A good way to remember this is for some fixed k value. Now you want to show that P of k plus 1 is true. And that's going to be the tough part. 4, you're going to make sure you write your conclusion. Write what you just proved. That's really important. P of 1 is often really, really tricky and difficult to understand. So let me go back and emphasize what this n equals 1, 2, 3, ... means. This means you actually have an infinite number of equations. So why don't we take a look at the equation called proposition of 2. So let's look at proposition of 2. Proposition of 2 looks like this. Is this following statement: 1 over 1 times 2 plus 1 over 2 times 3 is equal to, or is it equal to? Let's put a question mark there. 1 over 1 times 1 plus 1 over 2 times 3, is this equal to 2 over 2 plus 1? Now, how do I know to write 2 plus 1? It says so. So think of it as proposition of 2 says only add up the first two terms, and it better follow the pattern over here on the right-hand side. What would proposition of 3 be? The proposition of 3 would be add the first three terms and see if it is the pattern on the right-hand side. So if it's the first three terms, then n here would be 3, and that'll be 3 over 3 plus 1. Are you starting to see how there's an infinite number of equations now? What would proposition of 4 be? It would be 1, 2, 3, 4, and then you go over here and you wonder if this is 4 over 4 plus 1. What would proposition of 26 be? Proposition of 26 would be, let's add up the first 26 terms in this pattern. Okay, first 26 terms in this pattern. And then over here, you want to know if it in fact is 26 over 26 plus 1. It doesn't seem so obvious anymore, huh? Even this is not that obvious. And so that's why I put a question mark here. Why don't we do a proof of P of 2 really quick? Let's do a proof of P of 2 really quick. This is not part of the original problem, but it'll help you understand, what do we mean by a proposition for that many n values, for an infinite number of n values. All right, let's try this. Let's do proof of P of 2. And the way we're going to do this is we're going to prove an identity. And the way you prove an identity, you take the left-hand side and you want to show, in fact, it is indeed the right-hand side. And there's some work involved here. So let's start with the left-hand side. 1 over 1 times 2 plus 1 over 2 times 3. You cannot skip that step. You must write the left-hand side exactly once. Exactly once. Now we do the work. This is equal to what? This is equal to 3/6 plus 1/6, which is common denominator. So this is the natural thing you do. And then you even write 4/6. Now here's the unnatural thing you're going to do. Well, I'm sorry, one more natural step. The one more natural step is to write 2/3. Now comes the unnatural thing to do. You're going to write equals 2 over 2 plus 1. And notice this has nothing to do with equations. you're actually writing a string of expressions. You're writing one expression after the other. Expression, 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 expression. We got to the final expression. If we got to this final expression, then we write a period. And we make our conclusion. Therefore, P of 2 is true. Now, we've only proven the statement for one n value. How many times or how many n values do we need to prove this for? You only proved it for n equals 2. But it says how many times or how many n values do we need to prove this for? An infinite number of n values. You got to prove this for 46. You got to prove this for 4,862. You got to prove this for 2,642,841. So there are an infinite number of n values you're trying to prove this statement for. Now we're not going to do this for every single one. We're not going to go to P of 3 and do it. We're not going to go to P of 4 and do it. We're not going to go P of 5. We're not doing this in order. Just imagine if you're walking around a train of dominoes and you happen to step on the Kth domino. You're just trying to show it you actually made the K plus 1 domino fall next. So if you can do that, then we can guarantee that this falling of dominoes will take place and every single step will be true afterwards. However, to make this really work, it does say to start with n equals 1. So we need to find, or we need to prove, that P of 1 is true using this technique here. First, you got to be able to identify P of 1. How do you identify P of 1? Identify P of 1. In other words, write it out. State it. What are you trying to prove with P of 1? Okay. P of 1 is this equation. 1 over 1 times 2 is equal to 1 over 1 plus 1. Okay, is there really any work to be shown here? So in other words, are there even little red steps in between? Sometimes there isn't. Notice P of 2, you had to show a little bit of work. You would actually, write all this out and call that a proof of P of 2. We're going to go ahead and start the proof of P of n. And we're using principle of mathematical induction. The first thing you want to do is write 1 over 1 times 2 is in fact equal to 1 times 2. But we don't want to leave that to be 1 times 2. We want that to look like what? 1 over 1 plus 1. So I did add an intermediate step in between. And notice that is the left-hand side, in fact, is equal to the right-hand side. And with a little bit of work in between. There it is. Now what do we do down here? We put a period. And then say, therefore, P of 1 is true. Now, suppose the equation for a fixed k is true. Suppose P of k is true for some fixed k. You could even say a particular k. That is, what do we have now? And I'm going to write this in a different color. That is 1 over 1 times 2 plus 1 over 2 times 3 plus ... 1 over what? k times k plus 1 is in fact equal to k over k plus 1. We have that. We know that is true. Period. The other thing you want to do now is identify p of k plus 1. So notice I identified p of 2 for you. Then I identified p of 1 for you. Eventually, you got to be able to read this and be able to identify the statement p of k plus 1. We need to make some room here. Let's identify p of k plus 1. So we're at a point where you're off to the side, you're showing the work here, you got to identify p of k plus 1. What is p of k plus 1? P of k plus 1 is 1 over 1 times 2 plus 1 over 2 times 3 plus dot 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 plus let me start over. I'm going to start over really quick. I'll make it easier for you guys. 1 over 1 times 2 plus 1 over 2 times 3 plus dot 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 plus 1 over k times k plus 1 plus 1 over k plus 1 times what here? K plus 1 plus 1 is equal to what? Let me try that again. 1 over k plus 1, k plus 1 plus 1. What is this going to be equal to? This has to equal k plus 1 over k plus 1 plus 1, right? That's kind of like what we've been doing all along, so I'm going to follow that same pattern. Notice I wrote 1 over 1 plus 1 right there. 1 over 1 plus 1. So if I had to add the first k plus 1 terms together, at the end, the pattern should be on the right-hand side, k plus 1 over k plus 1 plus 1, which is what I wrote right here. That looks like a KH. I apologize. Let me write that a little bit bigger. There it is. Now, how come parts of it is in different colors? Well, you're going to see. You're going to see it. Now, how do you prove this? What is the left-hand side now? This is the left-hand side. You're trying to show the work to get to the right-hand side. You must write the left-hand side exactly once in your proof. So here we go. We're going to write it then, after the period. Then, we are going to write this. 1 over 1 times 2 plus 1 over 2 times 3 plus dot 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 1 over k times k plus 1 plus 1 over k plus 1 times k plus 1 plus 1. Now, we're stuck. That's where we're stuck. We are stuck right here. Remember, you're not talking about equations. You're talking about expressions. What can we do to this expression? Well, you look at the previous sentence. What does the previous sentence say? The previous sentence says this pattern here is another pattern. This pattern here is another pattern. We know that because in the principle of mathematical induction, we're saying that P of k is true for some fixed k. So replace this part with what? our next expression is going to be equal to k over k plus 1 plus k plus 1 times k plus 2. And now you're familiar with this. This is where we do our busy work. This is where we show evidence. We show lots and lots of evidence and try to get to the right-hand side. Okay, we gotta show lots and lots of evidence and try to get here. Our end goal is here, but this is the expression that we have to work with now. Now, I started writing something. Why don't I write it on a separate line to be clear? This is now equal to k over k plus 1. We need a common denominator. This is just like what you did with p of 2. If you go back and look at p of 2, you're going to realize this is exactly what we were doing even when you're proving the statement p of 2. You had to find common denominator. Now we got the common denominator, and this is equal to k times k plus 2 plus 1 all over the common denominator, which is k plus 1 times the quantity k plus 2. All right, I'll write this over here because I ran out of room here. Make sure you have longer paper so you can keep writing down. You should see only a string of expressions. Whoa. What do we have now? We have, this is equal to k squared plus 2k plus 1 over what? K plus 1 times k plus 2. And you're going to react to this, obviously. Notice you have a common factor now. And it gets a little bit easier as you're just writing all the algebra that you know. Now, instead of writing k plus 2, I'm going to write what? K plus 1 plus 1. And to me, that's good enough. I actually did skip a step by not writing parentheses. Technically speaking, there is parentheses here. And there's invisible parentheses on the numerator. And that would be even more clear, right? Remember what I said about the introduction to proofwriting? You're trying to write every single piece of evidence down. Now, I messed up on one thing here. I'm going to go ahead and let this slide. I'm going to let this slide right here. I'm going to say this is acceptable. K plus 1 over k plus 1 plus 1. I'll say that's acceptable. And did we do it? Did we show that this left-hand side you started with was right here? There's the left-hand side. And then you have to show that you have to show that you could work your way through your algebra and get to the right-hand side. And there it is. That's exactly what you wanted to show. You only could write the right-hand side exactly once. If you ever take trigonometry, you start to understand how to prove identities as well. All right, what does this mean? Therefore, what did you just show? Therefore, P of k plus 1 is true. Okay, therefore, 1 over 1 times 2 plus 1 over 2 times 3 plus ... plus 1 over k times k plus 1 plus 1 over k plus 1 k plus 1 plus 1 is in fact equal to k plus 1 over k plus 1 plus 1. Now I could erase this scratch work that I had. Remember, the scratch work was to identify p of k plus 1. In other words, you had to identify what you're trying to prove. You had to identify it. I could erase this now. I don't need this anymore. It's not part of the proof. It was just a scratch work. The final sentence is your conclusion. Oh, here, why don't I write another sentence so that I could emphasize that you finished step 3. Therefore, p of k plus 1 is true. Okay, now you can see how step 3 is true. Step 3 is done. Notice you did step 1 right here in this first sentence, or these first 2 sentences. Suppose p of k is true. That's part of the process. This is called the induction hypothesis. Show that p of k plus 1 is true, and that's where we are right now. You've just shown that p of k plus 1 is true, and then 4, make sure you write your final sentence. By the principle of mathematical induction, p of n is true for what? For all, emphasis now is all, n equaling 1, 2, 3, ... So all those infinite statements, all those infinite equations are actually true now. And you didn't have to write the proof an infinite amount of times. Oh, that would be painful, right? So we have to use this idea called principle of mathematical induction. Now, I typically end the proof with a tombstone. So you always label the beginning of a proof. Right here, I said it's the proof of p of n. And inside the proof of p of n, there's a short little proof of p of 1. You show that, and then suppose p of k is true for some fixed k. And then identify p of k plus 1. And of course, show the proof of p of k plus 1 is true. And then there you go, you have it. So in every principle of mathematical induction, you're really doing 2 proofs. You have to show p of 1 is true, and then you have to show that p of k plus 1 is true. So if you could put those 2 steps together, you have concluded that all the dominoes in that train is going to fall over and over and over again, and it will never stop falling. Let's circle the final answer. What is a final answer in a proof? The final answer in a proof is actually the entire proof itself. Do not skip a single detail. Your goal is to leave your doubters, well, don't leave any doubt for your math instructor. Let's just put it that way. Okay? You're trying to explain every single piece of evidence. Let's do another example here. Why don't we prove this statement or this proposition of n is true for n equals 1, 2, 3, ... by using the principle of mathematical induction. Now, don't forget, when you're proving something with induction, there are some steps here. 1, you got to show or prove that p of 1 is true. First thing you actually have to do is identify p of 1. P of 1 is actually harder because it's in some ways trivial. It's actually easier to identify p of 2. So if you need to, identify p of 2 first, and then go back and identify p of 1. 2, you're going to suppose p of k is true for some k value, or a fixed k, or you could even say particular k. Okay, it's just a fixed k value. And then 3, you got to prove, identify and prove p of k plus 1 is true, right? Identify and prove p of k plus 1 is true. So there's a lot of identifying to do. You got to identify p of 1, you got to identify p of k, and you got to identify p of k plus 1. Okay, so you got to know what you're talking about. And then, of course, the fourth step is write your conclusion. It's very important that you conclude what you just shown. That's only a short little sentence. All right, let's try to write a proof here. Proof of p of n. We gotta first show that p of 1 is true. If you're having trouble identifying it, you're not alone. P of 1 is often somewhat trivial. So what does p of 1 look like? P of 1 is this equation, 1 equals 1 squared. For this particular case, there's really not much work to show. If you want to humor yourself, you could write this. Note 1 is equal to 1, wanted to make sure to 1 times 1 is equal to 1 squared. Now you've shown that the left-hand side is indeed equal to the right-hand side. And you can only write the left-hand side exactly once, and you can only write the right-hand side exactly once. And then put a period. Then you say what? Therefore, p of 1 is true. Suppose, let me erase this now. Suppose p of k is true. So we need to write the sentence p of k. And the reason why we use the letter k is so that you don't get yourself confused with n. This one here is an n value here. This is n equals 1. Now this is saying what? This is not implying that n equals k. So now you're just saying some fixed natural number in your sequence, or some particular domino in your domino train. Okay, we're just going to pick that one. If we happen to bump it, we want to make sure it bumps the next domino. Now what does this mean? That is, we have this equation, 1 plus 3 plus dot 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 plus the quantity 2 times k minus 1 is equal to this pattern, k squared. You got to be able to identify p of k plus 1. So if you need to, identify it off to the side. Here, why don't I do this? Identify the equation or the statement p of k plus 1. P of k plus 1 is 1 plus 3 plus dot 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 plus 2k minus 1 plus bracket 2 times k plus 1 minus 1 close bracket. It has to equal some pattern. Equals what pattern here? It's got to equal the pattern k plus 1 quantity squared. So what you're trying to show is you're going to write this left-hand side exactly once, and you're trying to show that it is indeed this right-hand side, and you're only going to write this right-hand side exactly once. Let's start with the left-hand side. Let's note the left-hand side. Notice you are working with expressions here, not equations. I'm going to write an expression here. And now I'm stuck. That's all I got. That's an expression. That's a smiley face. Okay? That's an expression. What can you do with expressions? Well, we manipulate them. We change the way they look. You know, perhaps Bruce Wayne could dress up like Batman. Right? Change the way they look. So if you look at your previous sentence, there's a pattern. There's a pattern that says it's equal to k squared. I'm going to take advantage of that. This is equal to k squared. So you have to make sure you use your induction hypothesis. Plus 2 times parentheses k plus 1 minus 1. I'm stuck again. What the heck am I supposed to do here? Well, you just sort of react to it naturally. Now here, remember your goal though. Your goal is to make it look like the right-hand side. Your goal is way over here. You want to show this. You want to show that it's in fact going to be the quantity k plus 1 squared. Now it's going to take some work. And you know, that's math. So here we go. This is now equal to k squared plus 2k plus 2 minus 1. This is equal to k squared plus 2k plus 1. Now this is equal to, whoa, you know that trinomial, that factors, period. What did you just show? Therefore, 1 plus 2 plus dot 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 plus 2k minus 1 plus bracket 2k plus 1 minus 1 bracket is in fact equal to what? The quantity k plus 1 squared. Wait, this sentence is p of 2. Therefore, I mean not p of 2. This sentence is p of k plus 1. Therefore, p of k plus 1 is true. Ah, gorgeous. Final thing, we're actually at step 4 now. Okay, you prove that p of k plus 1 is true. Step 4, we're going to write a conclusion. The conclusion is really short. It's in one sentence. Therefore, p of n is true for all n equals 1, 2, dot, dot, dot. I should say by what? What principle are you using? By the principle of mathematical induction, p of n is true for all n, 1, 2, dot, 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 dot. Now remember, what is p of n? P of n is this statement up here. P of n is this sentence right here. It's that sentence right there. And you're trying to prove it for n equals 1, 2, 3, dot, dot, dot. In your proof, I typically end my proofs with a traditional tombstone. And circle your final answer. Remember, a final answer in your proof is actually the entire proof itself. You would have to circle the entire proof.